Good morning, ladies and gentlemen. Welcome to another exciting episode of Dave Does Math from Home. Today's episode of Dave Does Math from Home is interesting because it is a pretty much complete departure from what we were doing on the last episode of Dave Does Math from Home. In the last one we did section 4.5, which I described as peak derivative calculus. It's also pretty much the abrupt end of derivative calculus. There's really no good place to go from there. So we've decided to go to a completely different destination. Derivatives, fundamentally, are about rates of change and slopes and increasing, decreasing. We're going to leave all of that behind. We're going to do something completely separate. We are now no longer interested in rates of change or slopes or increasing and decreasing. We are now interested pretty much exclusively in area. We're going to take a curve, like, well, let's say something like y is x squared plus 1. This curve looks like this. Let's say I want to look at the interval between x equals 0 and we'll say that this is x equals 6. I want to find this area. That's what we're doing now. It's a complete shift from what we did before. So, in this section, section 5.1, we are not going to find this exact area. There is a technique later that we can use to find this exact area. It's pretty interesting. We're going to build up to that. Before we get there, we're going to start with, we're going to build up conceptually, starting with some slightly easier, slightly more accessible ideas. And the easier, more accessible ideas for approximating this area are going to involve Riemann sums. The shape you get when you do this area is not a reasonable looking shape. Like, underneath a parabola-ish looking thing is not a shape that we have area formulas for. If this were a rectangle or a triangle, we could use rectangle or triangle area forms. Even if it's a hexagon, we could invent an area of a hexagon formula without too much difficulty. But this is not any of those things. This is weird curvy shape on one end, but we got right angles on the other ends. So instead of finding the exact area of the weird curvy shape that we have accidentally created here, we're going to approximate the area of the weird curvy shape using the most basic area shape possible, the good old-fashioned rectangle. So the trick to doing this is going to be to split this into pieces. I'm going to split it into 3 pieces. So those 3 pieces are going to happen at x equals 2 and x equals 4. The interval from 0 to 6 in 3 subsections. So 0 to 6 is the length of our entire interval. We're going to split that into subintervals from 0 to 2, 2 to 4, and 4 to 6. And now, if you ignore the top edge of this, if you're looking only at the bottom and the sides of these things, the bottom and the sides of these things are pretty rectangular. Aside from the curvy top, you have right angles on the bottom and the side. And that's what we're going to rely on. We're splitting this into chunks of x-axis so that we can make vertical rectangles out of these things. And then we're going to approximate the area of this by finding the areas of these rectangles. The problem is going to come in when we start thinking about whether we want the rectangles to be above or below the actual function. So if we take this middle rectangle, for example, the middle subsection, for example, there's 2 basic rectangles we can make out of this. We could use the left endpoint and move right, and we would have a very short rectangle that underestimates the actual area of this thing. Or we could use the right endpoint and move left, then we have a very tall rectangle that overestimates the area of this thing. Advanced versions of this technique will try to use the midpoint as something that goes to the left and right. That doesn't actually provide us much advantage and is not very easy to do, so I tend to ignore the midpoint rules. I stick with either lefts and rights. We could also make a triangle shape. It turns out the triangle shape, because this diagonal line between the left endpoint and the right endpoint splits this thing directly in half, it turns out that the triangle shape, or the trapezoid I guess you would call it, the trapezoid, the result of doing a trapezoid is exactly the same as the result of using the right endpoint and the left endpoint and then averaging them, because it splits this thing perfectly in half. It splits the difference between them perfectly in half. So we're not going to do any diagonals. If we want that result, we can just use the left and the right and average them, and that'll be easier than trying to do trapezoids or diagonals or anything like that. And we might use midpoints sometimes, but not often. More often, we're going to do the right and we're going to do the left separately, and then we're going to compare the answers to kind of get a range, an approximate range of where this thing might be. So I'm going to start with using left endpoints to get these three rectangles. If I'm using left endpoints, then the points I'm concerned about happen when x is 0, when x is 2, and when x is 4. This x equals 6 is not going to be a part of my left endpoint situation. I'm going to erase this from the right endpoint thing so it's clear for now that I'm only using these left endpoints. If I'm only using left endpoints, then I need this point, x equals 0, x equals 2, and x equals 4. I do not need the x equals 6 endpoint. There is no rectangle to the right of that. It's not the left endpoint of anything. So I can ignore the x equals 6 for now. When I come back and do the right endpoint version of this thing, then I will need to use the 6 endpoint going backwards, and the 4 endpoint going this way, and the 2 endpoint going this way, but I won't use the 0 endpoint. So that's fundamentally the difference between the right and left endpoint version of this. So for the left Riemann sum, I have 0, 2, and 4 as my x values. The height of these rectangles is just going to be a y value. The height here is the distance from the x-axis to the y value at these x points. So all I need to do to find the heights of these rectangles is plug these x values into the function. So at x equals 0, I should get a height of 1. At x equals 2, I should have a height of 5. And at x equals 4, I should have a height of 17. These are the heights of my rectangles. The width of my rectangles is always going to be 2. I would like to warn you all right now, it seems a little silly to add a column to this table where every entry in the column is the exact same number. But I tell you from experience, when students skip this step, they almost always conflate the x values for the width. These x values are not widths, they are just positions. This tells you which y values you need to use to find heights. The x equals 4 rectangle still has a width of 2. It doesn't have a width of 4. You're not looking at this big rectangle all the way back to the y-axis. You're looking, everything has a width of 2. And I think it's very helpful to write that down. The most common mistake students make when doing this problem is they skip the width, they multiply the heights by the y values, which doesn't even make sense from an area perspective. So, make the width its own column, write all those down. That's always going to be, it's going to be a constant, and it's always going to be the length of your interval divided by the number of subintervals you're using. The book calls this delta x, the change in x. From one x value to the next, the change in those x's is 2 in this case. Also, I should say the book calls these values here x naught, x1, x2, dot dot dot, x sub n. So these x values are named with x's with subscripts, and these are called delta x. I tend to not worry about this notation. I feel like this is just extra notation that's not, I don't think it makes anything more clear. I think it's just makes everything feel more fancy, which is probably why the book does it. I will just call these x values in widths. So we have the heights of these three rectangles, we have the widths of these three rectangles. We can get the area of these three rectangles. This will be 2, this will be 10, and this will be 34. You get the areas of rectangles by multiplying width times height. So this is 2, this is 10, and this is 34. So the approximate area you get from this Riemann sum using left endpoints and 3 rectangles is 46. As you can see from the picture, 46 is probably going to be a really bad estimate. We're missing a lot of area here. And here, we're missing a little bit here as well. So, we're going to see what happens now if instead of doing left endpoints, we do right endpoints. We're probably going to get another pretty terrible approximation here, but we'll make it work. If we're using right endpoints, then we need to use the 6 and the 4 and the 2. So here's the neat trick about this. We already have an x equals 4 rectangle with a width of 2. This rectangle that goes backwards from 4 and has a width of 2 should be the same as this rectangle that we already did that goes forward from 4 and has a width of 2. And this rectangle that goes backwards from x equals 2 and has a width of 2 should be the same as this other rectangle that we started with that goes forward from 2 and has a width of 2. So these 2 rows I can keep. This is the x equals 2 rectangle. It's just going backwards instead of forwards, but it's the same rectangle. This one I can keep. I need to add one for 6. When I plug in 6, I will get a height of 37. And the width is still 2. Because I'm using left or right endpoints this time, I'm not going to use the 0 stuff. I'm just going to use these 3 now. And so this will give me a height of 74. Since now I have 74 on this rectangle, and 34 on this rectangle, and 10 on this rectangle, and I can add these guys together to get the right endpoint Riemann sum for this function on this interval in 3 subsections. So this will be 108, 118. So, once again, we can see that 118 is probably a pretty terrible estimate for this, because it's overestimating this by a lot, and it's overestimating this by a lot, and it's overestimating this by a lot. But we know for sure that these 3 are the left sum, and that was 46, and these 3 are the right sum, and that was 118. So the actual value of this area is somewhere between 46 and 118, which is not good bounds. One of those bounds is more than double the other. It's kind of crappy bounds, honestly. There's a huge gap between those 2 numbers. The exact area is somewhere in between these 2 things. it's probably pretty close to the average of these two things. I mentioned before that if you take the average of these things, basically if you split the difference perfectly in half, that's the same as like using trapezoids instead of rectangles. And a trapezoidal approximation here would be pretty close. It looks like it would still be a bit of an overestimate because this function is concave up, which means that the function is always below the straight line that connects two dots. So we're going to be overestimating still by a little bit, but not very much. So the average of 118 and 46 is going to be well, the sum should be 150, 164. So the average should be about 82. So the area beneath this curve between 0 and 6 is probably about 82. And that's an approximation. It's not a bad approximation. The question then becomes, how can we make it better? What if we want a better approximation than 82? Here's how we make this better. Most of the error we're getting comes from this big chunk of space that we're either not including but should be, or are including but shouldn't be. And we can reduce that amount of space by using more rectangles. So this one only used 3 rectangles. And 3 rectangles is not how you get accuracy out of this thing. What if we used 6 rectangles and cut this into more pieces? That's going to cut this amount of stuff that's either not included but should be, or is included but shouldn't be. That's going to reduce those things a lot. And it'll still leave us with some inaccuracies, but they'll be a lot smaller. So that's what we're going to do in the next video. We're going to do the same process with more rectangles. We'll do it with 6. We might try it with 12 if we get ambitious about having a calculator. So stay tuned for that. More is coming.